Is it on? Hello everyone, it is our pleasure to welcome Professor Tarun Saurabh of Raman Research Institute at IMSC for the Institute Colloquium. Professor Saurabh is the director of RRI and a senior professor working in different areas of cosmology and gravitation. He got his PhD from IUCAA Pune in 1995. After that, he was a postdoctoral fellow at CETA, Canada, and Kansas State University in USA. After that, he joined IUCAA as a faculty. In 2019, he moved to ISAR Pune as the chair of physics, and in 2022, he joined RRI Bengaluru as the director. In cosmology, Professor Saurabh has developed several crucial statistical methods and proposed important models for theoretical modeling and data analysis. Improved Richardson-Lucy algorithm and BIPOSH are the two such examples. He has authored and co-authored more than 250 journal articles. Beyond as a theoretical physicist, I consider him as a visionary. He built the Indigo Consortium and played the pivotal role in bringing LIGO to India. He has been the spokesperson of LIGO India. He also built the CMB Bharat Consortium collaboration that brings in more than 100 cosmologists in India. As the PI, he proposed ECHO, Exploring Cosmic History and Origin, to ISRO, a proposal for the next generation space mission for near ultimate measurements of the CMB polarization and the discovery of global CMB spectral distortion. If funded, CMB Bharat's ECHO will bring in the global efforts with ESA and NASA collaboration to discover the primordial B modes, neutrino mass, spectral distortions, etc. He is a fellow of International Society of General Relativity and Gravitation, Indian Academy of Sciences, National Academy of Sciences, and many more. He shared the Special Breakthrough Prize and Gruber Cosmology Prize with LIGO collaboration for the gravitational wave discovery. I've been very lucky to have Professor Saurabh as my long-term collaborator. Apart from being a collaborator at different points in my academic career, he has acted like a guide to me. So therefore, it gives me an immense pleasure to announce him as today's speaker. Today, he is going to talk about the validating cosmological principle. So without further ado, I will give the floor to Professor Saurabh. Professor Saurabh, please.
Am I audible? Okay, so let me begin first by, thanking IMSC for this invitation. And I understand it's during, just after you're celebrating your 60th year. At RRI, we are also celebrating our 75th year, so I know what it means for Institute and, how important it is to be a part of that celebration. So I'm really delighted to be here. I thank Professor Ravindran and Dheeraj for making this possible, and also Dheeraj for his very generous introduction. So I would like to talk about something that has been part of my research, one of the streams of research that I've been carrying out right throughout my faculty career, even before some of them. And this has to do with one aspect of cosmic microwave background that is not as talked about usually. Normally we know that the cosmic microwave background that you have is is like a plasma surface surrounding us. It's a sphere which is all around us. We are enclosed. Every observer in the universe will be, when they look out, they will find that they are surrounded by a sphere which is made of glowing plasma glowing at 3300 Kelvin. Okay, it's the expansion of the universe which kind of redshifts that Planck distribution at 3300 to something like a 3 Kelvin bath, which is what the cosmic microwave background is all about. And that was detected in 1965. And in this picture, then what the cosmic microwave background does, and it's amazing that nature has left this band open to us, so we can look to the furthest in the universe in the microwave background. So 14 gigaparsecs, if I, for non-astronomers, 43 billion light years. And this is the furthest you can look out in electromagnetism for any information, because when you hit a plasma wall, the opacity is high, and then any information beyond that, just like when you hit a fog, you can't see what is beyond the opacity equal to one surface. This is opacity equal to one surface. So from 65 to 92, this was the picture we had. We had a glow all around us. If the hot Big Bang was correct, then this glow was, numbers could have been a little different, but more or less, very soon after Big Bang, relative to our age now. So this surface now is about 380,000 years after Big Bang, and we are about 13.6 or 8 gigayears of age. So we are looking at a one-day baby. If the age of the universe, we are a 100-year-old universe now. And what is amazing is this radiation is largely coming through without scattering at all. So for people who realize this, that when you want information, you don't want it to be contaminated by other effects. And largely, again, apart from things that Dheeraj works on a lot, but I won't get into that at all, only 10% of the photons go through that, but not even 10, 6%. And then rest of it is what I'll talk about. Okay, so these photons are directly bringing to you information from a universe which is far in the past, the earliest moments of the universe, and it is also bringing to you information across the largest cosmological scales you can imagine. The causal thing extent, is only 3% more than this, although so it's just the end of the plasma. So in fact, this is fairly to scale. Okay, not to scale, but you can imagine this is very thin, right? Okay, so then if we of course have inferred a lot about cosmology, and I'll mention that a bit in the beginning, but then there are questions you can ask which are much more deeper. Okay, so what we have is what is known as the hot Big Bang model, okay, and which means that the universe started from a hot enough, hotter early and denser early phase. Now the cleanest and the most convincing evidence of that is the fact that when people studied this glow, in 1990 there was a satellite called the Cosmic Background Explorer, which looked at the spectrum of this of this radiation bath from 60 gigahertz to 600 gigahertz, and you can see that the measurements exactly threaded a Planck distribution, so much so that you can't see it to, I don't know, somehow it's looking a bit hazier, but anyway, the error bars here have been blown up by a factor of 400 to make them visible. So this is one of the most accurate measurements in astronomy that we know of, and this black body is much better than any black body that we know that exists naturally, as well as you can make in your lab. So people struggle to make black bodies over only ranges of frequency. But if this is correct, it means that in this plasma not only were photons and baryons in thermal equilibrium, because that would give you a Bose-Einstein statistics, but also that at some point the plasma was hot enough to have photon non-conserving processes, which is why the chemical potential is 0, which directly tells you that the universe must have been at least 10 million kelvins hot. Okay, that's not going to GeV scales or anything, but it tells you a 3 Kelvin universe was 30 million kelvins at least, and this is straight, you can read it off from here. Then if you believe in Big Bang nucleosynthesis, you can stretch it to a billion Kelvin, 10 billion Kelvin, and then depending on, I'm sure math science is full of people who believe in physics. Not believe, they work on physics well beyond that. If our picture is correct, then the universe has walked through all those things, phases in this past history, all in this area. Okay. And what happened, why this okay, now what happened in 92, I forgot to, sorry, I should go back. So this was one of the results of the Cosmic Background Explorers. The other one was that it was the first time in 1992 that we could detect slight fluctuations in the temperature. Till then, we didn't see any detectable temperature differences in the microwave background at different directions of the sky. So it is still a black body, but it's slightly hotter and colder. That has an implication for adiabaticity, but I won't get into that. But you could see that in this direction, the CMB is about 10 parts per million hotter or colder than the average, right? And then that was also another instrument on the Cosmic Background Explorer which did that. And then that was heralded as a big thing because of the following. If you look at our local, universe around you, we don't see a smooth universe, whereas our background cosmological model that we use assumes a smooth distribution of matter. Okay? Now, of course, you can average and then ask, how good is the average? But if they are really nonlinear structures, then there are many questions that you can raise about this averaging procedure and the metric you derive from it. So what is interesting is we believe these fluctuations grew due to Newtonian gravitational instability from tiny fluctuations. So the early universe actually was a very good approximation of Friedmann-Robertson-Walker model. Okay, and the microwave background fluctuations tell you that at a time when it was 380,000 years old, the universe only had fluctuations at the level of 10 parts per million. And if you then worry about nonlinear effects and all that, you will find that there's, at that time at least the metric is, absolutely unquestionably Friedmann-Robertson. Okay. And then if such fluctuations are there, and we also have been mapping out the distribution of matter around us, we've been measuring where the galaxies are, there are huge surveys happening, and then you can connect these fluctuations to that. And this is what we have been able to do in the last 3 decades very well, starting from the first discovery of this fluctuation, 92, to now, and even continuing now. Okay, and we have made immense progress. But there is another sector, and I think which will be more interesting to the math science community, is largely untouched. What happened? Sorry. So we do use these fluctuations and connect it to the current universe and get all our whole limits on the cosmological model, and the fact that we talk about a standard cosmological model within quotes maybe, is because we can do this very well. But there's always the question of what generated those tiny fluctuations in the first place. If you really look at the length scales of correlation, they appear to be acausally connected, in a standard Big Bang model. So if you want to correct that, you have to invoke something like inflation. And we have guesses if something like that happened in the early universe, then again, people like Dheeraj are experts in that. You would know that it generates density perturbations as well as gravitational waves. And then you can look for the density perturbations, then are the same fluctuations that have given rise to the galaxies here. And then we can understand that science. And I won't talk on that thread of work, but Dheeraj has been involved in parts of that with us. But the important point I wanted to mention here is the testability of early universe, through CMB opens a huge possibility for high or ultra high energy theorists, because there is no other option of experimentally kind of verifying your theory. The cosmos gives you a playground where this is, you're guaranteed that if your theory is right, then that physics must have played a role. And then you can look for effects of that kind. Are there any unique effects, right, that you can, we are missing because we are not looking for it. And that's a theme of activity that I was doing, rather than just focus on this connection and get better and better cosmological parameters. That, we have done to death. So that's one stream. The other stream is we have the universe on the largest scales, and we built our cosmological model on certain assumptions, right? The first, and then are we really sure that those are valid? Okay, so let me just give you an idea of how things have progressed. So this is the cosmic background explorer I talked about. This is when I started my research, by the way. This was, when we wrote we wrote the first paper from India on the cosmic background Kobe results. And then next decade was WMAP, where some of the people started working, and towards the end I think he started, and then we have another decade of Planck, and so 3 decades of data getting progressively better. And these are the milestone missions, space missions, but there have been lots of experiments on the ground which have done a lot of interesting things. Now the question is, what have we done? So if you want to really be a bit business-like, what good did CMB do? Okay, so here is what it did. So if you look at the figure of merit, which basically tells you how much information have we added about cosmology, okay? The factor here is about 10 to the power 9 over these 3 decades, okay? And this is a fairly, very quantitative, analysis. So if you look at the Planck final paper, they point out that even in the most, kind of conservative thing, it's at least a factor of 10 to the power 7 to 10 to the power 9 that you have added, or 10 to the power even 13, which you have added as information about the universe, model of the universe. So this is just to tell you the faster than Moore's law, right? So this is an extremely successful field in yielding results about cosmology, okay? And the question is, are we done yet? We are not. So the Planck, which I told you, is the biggest repository of measurements now, all sky and a few frequencies, is fairly out of date. There are experiments which are already running with much higher sensitivity from the ground. And as Dheeraj said, there is interest in launching a next generation CMB satellite, which will just kind of wrap up the field. Okay, that's very important. And this is where we, this is 2020, so this goes on, and it's a relentless march. Okay, so what have we learned? So this again, depending on which generation of student you are or faculty you are, may be interesting or not, but these are the cosmological parameters. So we find that this data about the cosmological model that we, or the inference that we can draw about the cosmological model from that current Planck data actually gives you amazing, measurements of the parameters. Now remember that I'm always emphasizing that there's a model, cosmological model, which has parameters, and there's data, and you can constrain it very well. Okay? The point is, you might say, oh, what's the point? Why are we digging here? Because when I started, this number was known to a factor of 2, okay, 3 decades back. Okay, now we are fighting over this number now, which I guess, again, is a part of the activities going on here. But this was a factor of 2, now this is 1.3%, and it so happens that there are certain measurements which are not matching, but anyway. But these are numbers which are absolutely mind-boggling. So it's, just to give you an idea of that, when I was in my 40s, I often came up against some broader community of faces presenting cosmology. And when I showed a chart like this from WMAP, someone said it's not possible, right? Very, very senior physicists. I said, no, it's not even my work. This is the story in cosmology. Because cosmology, we have always known as a, kind of a semi-metaphysical kind of thing. You can build any model you want, you can do anything you like. That's no longer the case. Almost any deviation that you want to build out of these models have such severe constraints that, from various things, not only cosmological background, from many, many observations. So it's a very exciting time to be in cosmology. And the important thing about the cosmological model, as I said, I always put it in quotes because it's not like the standard model of particle physics. Okay, this model is also built upon symmetries, but not as acutely as the standard model and of particle physics, and we need to really figure out whether those symmetries are there. But we believe that the cosmological model, if it is one of the Friedman-Robertson-Walker, then we know for sure that the Friedman-Robertson-Walker model has flat spatial hypersurfaces. It is dominated by a fluid which we don't understand. A good guess for that is like a cosmological constant. So I belong to the community when, unless shown otherwise, I would believe the simplest explanation, which is a non-zero cosmological constant. And there's cold dark matter. And there's a primordial power spectrum, which we expected to be scale-free, and it's almost nearly scale-free with a little tilt, which is also important. Okay, so this is where we stand now. And then this probably, is a decade old. Like we started believing, a lot of articles got written up. I mean, even 2004, the standard model. But we need to check every every tenet, fundamental tenet on which we have built this model. So one of the fundamental tenets is that we believe that there's a hot and dense early universe and this thing, which we have checked to a large extent, but there's a lot more you can do. So, so when we talked about ECO, it was a cosmic history, which is, the CMB spectral distortions can tell you a lot quantitatively about how the universe went through different stages of temperature. Okay, the other important thing is we believe that the universe obeyed something called the cosmological principle. That around every observer in the universe looks the same at all directions. Okay, on the average, but that's important. So that isotropy should be interpreted as statistical. And then the question is, how far can we go and pin that down, right? What possible things that we can measurably print, pinpoint. So there are things like, of course, theoretically you think inflation will do this, that thing. But ultimately the arbiter is measurements. So how far can the data now query these assumptions? And some of them, some of the work has also, like, the CMB fluctuations. I told you of the story of the plasma screen, and these fluctuations are actually, can be understood as fluctuations on the plasma. And you can use standard plasma physics to understand them. But the question is that a fairy tale or is that real? We have grounds for independently checking that. Again, that's not going to be part of the talk, but CMB polarization, baryon acoustic oscillations have allowed us to do that. I told you that the tiny fluctuations that we see in the radiation of the universe grew to become this, nonlinear structure of galaxies, superclusters, and clusters of galaxies. Is that again just wishful theoretical thinking? Because we believe Newtonian instability is enough. Right, but now we can actually probe the inhomogeneity that is created as a function of time using weak lensing of the microwave background itself. Planck has been able to do that, and we believe that this is fairly consistent with the structure formation theory as you would expect in a flat lambda CDM model. Okay, so that's why we keep going back to this model. So there is something to stand on in cosmology. Now we have a model which seems to be fitting everything that we see. We don't understand much of it, but that's notwithstanding, we have something to stand on. Okay, then there is this paradigm of initial conditions. I told you that something perturbed the universe in the early times, and we have a thought about that. The question is, how far can we show that that happened? Okay, that is basically this paradigm of inflation, but there could be other things. But the point is the data is good enough to check this out. Okay. So with this background, my talk today will just focus on one of the streams, which is this paradigm of isotropy. Okay, and This is, as I said, a predicate of cosmological principle, which was used to build the first models of cosmology about a century back, right? And Einstein used it, every other people said, it was simplicity, right? Just let's start with the homogeneous, and it's the simplest problem that you can solve in GR, because you've got homogeneous matter, and there's nothing easier than that. And then the question is, how well can our current data tell us this? So again, emphasizing that the cosmic microwave background I told you is data which is coming from the largest, it's coming from a screen which is surrounding us as the largest distance you can probe using electromagnetism. So 43 billion light years. So I have that sphere, I have fluctuations on it. If I want to overall gauge if the universe has isotropy violation or not, okay, those fluctuations and the fact that they will be invariant under rotations of the sky is an important way to check. And we have such excellent data that it has become a real possibility to address this problem quantitatively. I can tell you what level can I put limits on any deviations from the fact that the universe is the same everywhere, right? And this comes from a very simple thing. You have a sky map and you go to harmonic space, then you have harmonic moments, just like Fourier modes of a field, right? If the field is isotropic and homogeneous, as many of you would know in field theory, then the K modes are uncorrelated, right? So here similarly, the LM, which are the radial and azimuthal modes of on the sphere, they are uncorrelated if the universe obeys statistical isotropy. And to put it in an observational language, from the data I cannot infer anything more than this angular power spectrum. Or another way to put it, I can give you the same cosmic microwave background in rotated coordinates and you will not see any difference. You can't predict, you can't infer anything very different, because if you do that, that means there's a direction. Okay, so that boils down to the fact that there are no off-diagonal correlations in the spherical harmonic coefficients. But then there are models in which you can predict such things. Like if the universe has a global cosmic topology, as many of you know, it can be isotropic and homogeneous, but yet wrapped up like a torus or even more complicated thing. There you get information. You will detect it in off-diagonal information that resides in the off-diagonal. And the point I want to make is, still now we have been only focusing on measuring the diagonal because we assumed this. So now the question is, can we now look for these? And that has been the program of research. So this is something that we did, with using something which we call the bipolar spherical harmonic spectra, which is essentially a total angular momentum representation of these ALM, AL prime, M prime states. Right? In quantum mechanics, you do the total angular momentum representation. It's the same thing. And then these, because they are summing over many modes, are measurable from a single map of the sky. And that's very important to realize, that we have only one sky map, hence we have to create things that are measurable, right, by averaging over modes. And this thing mathematically is the most natural generalization of the angular power spectrum. Okay, so just for people who want to look at it more in a big picture way, till the bipolar power spectrum, what we have been doing is measuring one of the possible power spectra that you can measure out of the CMB map, which was the angular power spectrum. But that is the L equal to 0 case, which is the isotropic part of the power spectrum. If there are violations of statistical isotropy, you can measure deviations, statistically significant deviations in many of them. Of course, you can't do every of them or up to infinity, because you're limited by information. But the point is, you can measure these L equal to 1, total angular momentum equal to 1, 2. And the interesting thing is why this representation also is cute is because it is directly transferable to the angular scale on which you have patterns in the correlation function. When you're saying that the correlation function is not isotropic, so 2-point correlation function depends on which two directions you're looking at, not just on the separation of the directions, then there is angular scale to it. So this is the inverse angular scale associated with it. So you can, so if you want to just look at the mathematics, we were dealing with isotropic correlation function, which means if you have two directions in the sky, the correlation only depends on the angle between them. So it's a cos theta thing, and everyone knows that you do a Legendre expansion, and then the CLs are just coefficients of that. But if this was not true, if they independently depended on the two directions, then the most general expansion is the bipolar spherical harmonics, and these coefficients turn out to be these total angular momentum states. Okay, so it's a very natural generalization and a natural basis in which to look for information beyond the angular power spectrum. So then you can construct various things. You can measure these. You can even average further and get something which is rotationally invariant, but still, if this L script L coefficient is non-zero for L greater than 0, then you know that there is a violation. You may not know exactly which direction. For that, you have to go back here. Okay, something happened. Okay, yeah. And then you can also have visual representations. I won't, so you can make maps of the correlation function anisotropy. And they, in this case, doesn't look very, these are actually from the data, WMAP data. And we were looking for any statistically significant, deviation that you can see, okay? And it's obviously, if we had seen, you would have known. So we didn't see anything statistically significant. You always see things, but you don't, important thing is. So the question is, what kind of questions can this kind of a formalism, which is looking for violations of statistical isotropy, answer? Right? For cosmology, for example, you can have a Friedman-Robertson-Walker model because the local geometry does not dictate the global topology. You have nothing that you can say about the global topology. The only best chance of doing that is to look at large scales, and the largest scales are proved by CMB. So you can say if there's a global topology, non-trivial topology, on scales of 43 billion light years. Right? Or, actually you can do it till 120 billion or something, up to pi kind of thing. Okay, so then that's one. You can ask, Friedman-Robertson-Walker is one model, but if you remember in history, people wanted to get rid of the singularity, and then there was a lot of interest in anisotropic models of the universe. So these are the Bianchi models and all that. You can ask, is there, okay, it's not obviously a Bianchi model, but is there a slight bit of anisotropy in the expansion of the universe? You can actually put quantitative limits on that. Any other global symmetry, magnetic fields, whatever, global magnetic fields and things like that you can think of. In addition, there are few effects which we know will exist. And that's a nice way to also calibrate that your method works. So one thing is we are moving with respect to the microwave background, we believe, because the CMB has a dipole which tells us that we are moving at about 380 kilometers per second, enormous velocity with respect to the cosmic rest frame. And that not only gives you this dipole, which is obvious, Doppler effect, but also gives you this subtle special relativity effect of aberration, which the current CMB data is sensitive enough and has the angular resolution to derive, right? So this is started happening. And similarly, weak lensing, which is the, we have a structure around us, and given that, obviously given the lens, which is lensing field that is around us, we will have a particular form of isotropy violation. and that is also measurable. Similarly, epoch of reionization, if there are inhomogeneities, you can use this formalism to measure it. Another important thing is we always worry if the experiments are doing fine. Is there a contamination from foregrounds? You can do that. Is the noise really well modeled? Noise is always inhomogeneous. It's not the same across the sky, but the question is, have we been able to model it out right? If we don't, then it will show up in the biposh, right? And then one thing that we actually showed, which I will not mention here, is that we showed that the WMAP could detect 1% non-circularity of its beam response function, and that it did so at few sigma. They themselves discovered it, but they just said, okay, there's some systematic effect, but they didn't, they did the biposh formalism and they saw this effect, but did not bother to answer it. But we later showed that if you model the beams, the non-circular part of the beam, it's not really circular at 1% level, and that exactly reproduces what they measured. So this is how I feel that this is an important new area. So let's look at beyond the angular power spectra, and I'll quickly go through a historical thing. So one of the early questions I asked with my student Amir Hajian was, is the universe compact, right? So it could be toroidal, more complicated spaces. And then we had actually looked at specific models, and you can do a fully Bayesian kind of a thing to look for whether that model is done. So we've obviously found null results, but roughly we could say that the universe was, you had no topology where the spatial volume of the universe is much greater than the volume enclosed in this horizon size. Okay, that was a rough demarcation we could say. But this is way back, right? This is even before I was a faculty here. Okay, and then there were various times, various models came into the picture, global topology as a torus. Then there was a time when, there was a Nature paper which said the universe is a Poincare dodecahedron. Okay, and they were very confident about it. And then there was a time when people thought the universe was negatively curved, and to explain the isotropy and homogeneity, you have to assume that the universe was a compact hyperbolic space. In all of these cases, you can model it. You can then check against data how to do it. And there are very interesting stories about how we looked at the correlation function in hyperbolic spaces, compact hyperbolic spaces. Similarly for him. But I'll just quickly say that there are very distinct signatures. And remember this kappa L that I showed you, and for different topologies, right? And then you can measure the same thing in data and ask, is that valid? Okay, so this for some reason remains a Astro PH thing. You can see that the Poincare dodecahedron we really went after, and you can show that as the curvature of the universe is increased in the spherical domain, you can see that this signature rises, right? And particularly for the best fit number that they quoted, Poincare dodecahedron with the total energy of total density of the universe being 1.013, you can see there's a huge signal, and this is measurable. So this is, we showed that the current data should be able to see it, okay? And okay. Similarly, you could ask, there was, even when Planck came out, they looked at fits to Bianchi models also, not just and there was one model which actually reproduced some of the features of the global structures and the fluctuations, and this was a Bianchi model. Now there were people there were papers which says, oh, rotating universe after all, right? And this is a reference there. So we again went back and so there are lots of rotation patterns possible. But in general, if you hide a Bianchi template, this is work that Tuhin Ghosh, who is a faculty at NISA, did as a master's project with Amir Hajian. You can hide it in the fluctuations and it won't really show up, obviously. But if you measure it, you can put limits, going the wrong way. So you can show that you will have a measurable power spectrum, and then you can ask, do I see it in the data? And then you can put limits on the shear parameter of the Bianchi model. And these limits were the tightest at that time. I haven't kept track of the literature to see if there are stricter limits, but we put these limits out in 2007. Now I'll come to more recent stuff which we did with Planck. So one of the puzzles in the CMB world has been from the days of Kobe, that if you look at this map, Kobe saw fluctuations but not at high resolution. So it saw something like this. And some people remarked that if you really cut the sky into two along this line, the fluctuations on this side are markedly higher than the other. In fact, if you do that, you find it's 14% stronger actually in amplitude, the fluctuations in this half versus that half. But during the Kobe time, the whole thing was okay, we will have foregrounds, we may have all kinds of effects, it's a first experiment. It persisted in WMAP, it also persisted in Planck. Okay, and that's when we were invited to join Planck to really look at it quantitatively with our measure. And we did show that if you look at the universe on the fluctuations on the largest angular scales or the lowest multiples up to say 64 or something, you do see a deviation at about 3 sigma. Okay, and then you can represent it as if you have a statistically isotropic sky but modulated. Now the reason we had a empirical phenomenological model is because there is really no theoretical model which can explain a capital L equal to 1, and I can discuss with any of you why. It's extremely difficult to get theoretically this thing, but so we did it as okay, let's just put a dipolar kind of a modulation here and then ask how big is the dipole and which way it's pointing, and we could reconstruct it. Okay. And again, this is basically the status of theoretical understanding on it. I won't really get into it. And this is fairly old. I stopped worrying about it after 2016. This is the list that Shubhadeep made of all possible ways people have tried to explain this L equal to 1. And we really don't know what it is, right? So we are in this situation, and that's why we have a phenomenological model, right? And I can tell you why theoretically it's difficult to model it. So we have this phenomenological model where there is this isotropic sky which is modulated by a dipolar function, and we try to get its amplitude and direction of the dipole. And if you put it and do it in the Bipoche formalism, as I told you, that you see this effect at about 3 sigma if you compare this stick here, and only at the low multiples. So as you look at the maps at higher and higher resolution, this thing sinks within the uncertainties. So this is what happens when you take the cumulative thing. When you retain only the large angular scale modes, it's significant. But as the rest of all it's saying is the largest angular modes have an anisotropy, but the smaller angular scales do not, right? So it doesn't carry over. And you can also infer the direction. The reason the direction is important is the following. This direction that you infer, this or this, depending on WMAP or Planck, does not really correspond to a known direction in the universe. See, if it was the south ecliptic pole, then you would have, the Planck scanning strategy has a north-south thing. So you might say, okay, there's some systematic effect. If it was somewhere related to the CMB dipole direction, you would say, okay, something is there. Okay, you might worry about something. But here this is at least not associated with any known directions that we are aware of. Okay, and then with Planck we had the ability to look at this effect at separate frequency maps. So now if it's a foreground effect, you expect it to depend on frequency. CMB being a black body, in terms of thermodynamic units, it is achromatic, and you see that. In all three of the frequencies we see the same effect. Okay, and then as a part of the collaboration, we just set out something called a p-value, which is probability of this happening by chance in random realizations. So it's not astounding. It can happen 6 times out of 1,000 by chance. Okay, now it's not something that we will lose sleep over, but on the other hand, it's interesting. It's not even a p-value which is comforting that way. So this was the story up to the Planck collaboration, where we were part of it, and then the question was, this was a deviation from statistical isotropy, but if you look at Planck, all results about the standard cosmological model were not given in terms of a particular measured sky map and the best sky map. It was the most likely sky map given the data. So it was all done in a Bayesian posterior manner, and we were quoting the numbers that we are quoting were maxima of the posterior. So the question many people asked is, you're saying 3 sigma, but how do you know what the how the probability distribution is? How significant is it? So we wanted to do a fully Bayesian approach to looking at things beyond the angular power spectrum. For angular power spectrum, Planck already did it. So we developed a method which gives you the maximum of the posterior, but including both the isotropic and anisotropic part. Okay, so this was developed by Shantanu Das, Ben me in 2016, and then the next generation of students with Shantanu, we tested it on data, right, Planck. So let's see what we got. So we again, you have actual Planck data. So this is just to tell you, although we think we have a beautiful all sky map, Planck shows you a global cosmic ball and all kinds of things, there is some contamination here, so you have to hide it. Now if I hide a portion of a sphere, I have already broken isotropy, right? So that you have to account for. I told you that the noise varies from different region to region of the sky, and this is the pattern in which, it's a very complicated pattern in which it varies, but you can model it. So all these were taken into account, and we also enhanced the phenomenological model. In the previous model, the dipole amplitude was non-zero up to a particular L and then went to 0, because we knew that only existed in low L's. Okay, but here we actually had a power law fall off, and so L to the power of some alpha. And it's interesting that when we did our whole thing, if this is the posterior distribution of alpha, and it actually peaks around -1, okay, some 0.992 or something. But it's interesting because there are physical effects of the microwave background which, relative to the primary fluctuations, falls off as 1 over L. One of the most well-known one is the integrated Sax-Wolf effect. So if there is something physical hidden there, maybe it's telling us that. Okay. And then we did what you can do now that you have a posterior. You can ask for a Bayesian odds of a model which has this effect and a totally statistical isotropic model. Now if you look at the Bayesian Bayes factor, and you can use this Savage-Dickey ratio in this approximation because it's a nested model, and you find that this is about 0.25, okay, in favor of the statistical isotropic model. It's not 10 or 100 in favor, which is what you expect if it is most definitely a statistical isotropic model. But it's not also so small that you would say that there is an obvious problem with our cosmological model. Now this is interesting. The question is, will this improve any further? Not with the temperature fluctuation anymore. Planck has measured them to the best possible thing. And at the largest angular scales, we are limited by cosmic variance. Okay, so things should not, unless there were systematic effects, things cannot get statistically better. Okay, but the hope is there are independent measures of such distributions which you can look at, like the map of the mass, integrated mass distribution that you get from weak lensing, or the polarization in the microwave background, or many other things, where you can look for something which is showing you the same effect. Okay, so then I'll quickly go over something which is even more recent, and this is an interesting story. As I told you, that we believe we are moving at 380 kilometers per second with respect to the microwave background. Okay, so the cosmic rest frame, and we are moving with respect to that. So that's a beta v by c of 10 to the minus 3. Not a very large effect, but remarkably, Planck in 2013 already showed that because this kind of velocity would induce a relativistic aberration, and relativistic aberration on the sky actually bunches the sky towards the direction in which you're moving and rarifies the sky behind you. Right? This is what happens. So this is of course an exaggerated picture, but as you increase beta, you will see that more of the sky keeps coming in front of you. So you magnify as well as you're doing remapping at L equal to 1, right? You're moving directions forward. Okay? But it is at 10 to the minus 3. But Planck had the sensitivity to see it, which is an amazing story. So Planck wrote a paper saying if you really infer the velocity independent of this dipole that we see, the number you get is consistent with it. But since this was taken to be a known, obvious thing, there was no effort put into making it very statistically high significance or anything. It was more like, okay, we have cross-checked that it is there. Okay? But then there came this paper where Subir Sarkar was also involved in this group. And Subir gave a talk during the pandemic where they had these results of looking at our motion with respect to distant quasars. And their inferred velocity of motion was almost twice of what we expect from the CMB dipole. Okay, and then they sort of said this are in conflict with the cosmological principle of foundation. So I remember asking him during that talk in the pandemic, but we have measured relativistic aberration. That's an independent way of showing that the velocity is consistent with the kinematic velocity, right? So it has nothing to do with whether the dipole is intrinsic or all due to this. But the thing was, but that was shown only at some 3 sigma plus or something like that. Not really. But I knew, because we did this just to check our methods, I knew that the data can give you a much more significant result. So we got together with my students, and we just worked it out. So this is very standard stuff which any of your undergraduate students can be given a problem of how does the CMB sky map under a Doppler boost. And you can work out, and you will find that there are off-diagonal correlations at capital L equal to 1, and then you can look for it, okay, in the data. And we did that in a totally Bayesian way, and we could show that at 5 sigma, this is the posterior, which is consistent with the measured dipole at 5 sigma, okay? And it is inconsistent with twice its value at an enormously low thing. See, if this is about 1, at 2 you can see there's hardly any weight, okay? And then we could also infer the direction, which was largely consistent with the Doppler boost. Remember that the dipole gives you a very accurate measurement because it's a millikelvin effect. Here obviously, uncertainties are larger, but nevertheless a totally independent check. And so this is what we did. Again, the base factor is what people want to do that. So we said that there's significantly large base factor in support of a dipole origin or kinematic origin of the dipole that we see in the CMB. And what is seen from the quasar, at least with the Planck data, is ruled out at a base factor of 10 to minus 11. Now, I am not here to say that whether the quasar analysis is right or wrong, but there are two ways of looking at your motion. In the case of CMB, we can really make sure that because of this aberration effect, you can clearly make sure that it's kinematic, because we don't know of any other effect of that kind which can be, and we have to, when we know that special relativity will give you that effect, and if it accounts for the dipole, then you don't need to really worry about anything more. So this is where I'll stop, and then we are obviously trying to understand these much better. So the question is, where does the signal in this Doppler boost lie? So we have got it at 5 sigma, can we get it at 8 sigma, and then nail the whole thing? And the question which was not too clear is whether going to higher and higher resolution CMB maps will help. So we actually recast this whole bipolar spherical harmonic thing in real space, in terms of real space correlation function. So interestingly, and rather, it sounds like a contradiction. We look for anisotropic correlation functions, but we represent them in terms of a set of isotropic correlation functions, and that has certain advantages of, if you don't have to go to harmonic space, because most of the experiments now are not full sky experiments, they are on the ground, right? They can't see the full sky, and so harmonic part, you always have a cut sky effect, right? You don't have the entire sky, so YLMs are not complete, whereas this correlation function doesn't suffer from that. Right, so we have started, so this is how the Doppler boost looks. I should have added them, but the students have now worked out how various other isotropy violations look in this kind of picture. And here what is clear for the Doppler boost case is the effect actually is detectable as you improve the angular resolution more and more. So this is small theta. And you can see the distinction between this, which is isotropic, versus these, which are anisotropic correlation functions, actually exists in the small theta, which is large L. Okay, and that is why W map, which had a resolution here, versus Planck, which had a resolution here, Planck could measure this, whereas W map couldn't. Right? Anyway, so let me talk about this health report. So the health report of the cosmological principle. So there is this dipolar modulation, the CMB. It's something which is phenomenologically, if you put it, it is there. It is a 14% effect, amplitude square, and it is seen in a natural basis. You're not using a designer statistics. It's the most general natural mathematical extension of the angular power spectrum, and you see it in the L equal to 1. I should also mention that we looked for all the capital L's from L equal to 1 to 32, and this is the only L at which you see a significant deviation. We did a Bayesian thing, and best available CMB data do not rule out a non-CMB, non-statistical isotropic sky. But I'm not saying there is a non-statistical isotropy, but it's interesting that it doesn't. So maybe there is some signal here which you look for in CMB polarization and weak lensing maps. And our motion with respect to cosmic rest frame, though, seems to be entirely kinematic as far as we can understand from CMB. Okay, so I will stop here and take questions. Thank you.
Hello. Thank you, Professor Saurodip, for the great historical overview and the present status report of the cosmological principle. Now, the floor is now open for questions. Sorry.
I wanted to ask you, you mentioned about getting signals of this inflationary phase in the CMB. So what part of the spectrum would one look at to get some information?
Again, it is at large angular scales, but not the largest. So it's between multiples of 70 to 140 that you would see power in the B mode. B mode is the kind of parity non-conserving part of the polarization. So if you take a mirror symmetry, it doesn't look the same, mirror image. Okay, so these are world-like patterns that you expect to see in the polarization. So these can be generated by gravitational wave. These cannot be generated by scalar perturbations at linear order. That's because scalar fluctuations don't have any way to create a handedness, whereas gravitational waves are shear field, so they can. And that we think would be extremely convincing if we see a shear. So I should say, I mean, the polarization can have a shear part and a non-shear part. We have seen the non-shear part very well. The shear part we have seen, which has been generated by weak lensing, but that is at smaller angles, which is higher multiples. That we are now routinely measuring. But at this intermediate multiples of 70 to 140, that part is kind of, known effects are low, and the only thing that can fill that up is primordial gravitational waves from inflation. And that is something that we really seek to measure.
Also, if in the inflationary phase there are other particles apart from the inflaton, like the fermions, and there is a strong magnetic field, there can be some shear created due to that.
Yes,
so can one measure different models there using those data?
We could, but the point is that what redshifts are they created and how long have they persisted? So although I said we are going back, way back into the universe, but the time that is, at which the energies are comparable to the kind of maybe scenarios looking at, it depends whether those persist to the microwave times and effect. But it is true that neutrinos, the fact that neutrinos are there, actually neutrinos are a source of shear, and we measure it, right? So that is there.
Thanks for the excellent talk also.
Thanks, nice talk. I want to ask about this motion, our motion in cosmic rest frame. We are also involved in a revolution and rotation, which makes us, or which allows us also scan the sky from different perspective. So if we make a 24-hour scan over the sky all the time, so we will have different kind of aberrations, right? So will this affect your analysis?
Okay, yeah. So are you asking me the motion of the satellite
so
itself?
along with the 380 kilometer per second thing?
So obviously there are many motions. The Earth moves at 30 kilometers per second. Satellites, are more or less in that ball figure. This is 380 kilometers per second. Okay, so that's
it's a small effect, but still, since you are rotating, you get to see the sky from all directions in different times, right?
No, so we can see the entire sky. See, we can't see it from all directions. We are seeing the sky. Sky is painted, it's a celestial sphere, right? So fact is, whether I'm sitting on this, thing, which is the Earth going around this, the Sun is going around the galaxy, all these velocities are there. But the most dominant thing is our galaxy falling into the Virgo cluster at about 600 kilometers per second. Okay, so that's that's because of scale that this is a dominant effect. If it was at tens of kilometers per second, we would have had issues.
Okay, thanks.
Hi, thanks for the talk. So what is the future scope for 21 centimeter cosmology to help with constraining some of these inhomogeneities and like maybe breaking of isotropy and other things?
Yeah, so that's maybe I should have added that. Once we start making neutral hydrogen maps up to redshifts of 30 or 40 with maybe experimental setups on the moon and things like that. People are thinking about it. It's not a joke anymore. Then that's another measure of isotropy violation. Okay, because you'll be going back. The epoch of reionization, I am a bit worried because it's a very complicated physics that happens. So I don't know whether it can be neatly, connected to something like this. But yes, I mean, just like any time you get a frame around you, screen around you, you can measure your motion with respect to that.
Okay.
So if you get the, screen like the reionization screen, you should be able to dig out this thing, or if you look at neutral hydrogen maps, you can do that. And I think that's the future. Because cosmological background, for all its greatness, and you can see how important it was, but it is limited to a sphere at a particular. But neutral hydrogen maps you can make at different spheres, right? And that is lot more modes, lot more information. So that is the future, but we aren't there yet. But it's certainly something young people should keep in mind.
And one question, so you talked about scale free, so that means that the spectral index, right? I think when you refer to that, okay.
Yeah, it says basically, if the inflation was, a de Sitter is a good approximation to it.
Okay.
In a de Sitter universe, the fluctuations are scale free because there is no, there's no time, there's no fixed, scale in the de Sitter thing is too much symmetry.
Okay.
So there can't be any scales at which the quantum fluctuations are different. Having said that, we know that the universe didn't inflate forever. De Sitter does. So the fact that it breaks means it cannot be exactly that. In fact, we know from the data at 5 sigma that it's not exactly scale free, and that's very important. Okay, exactly scale free, actually you have an infrared divergence. So in fact, it's not even a physical number you'll get, so you need a finite period to de Sitter space, but it's interesting that we are very close. I mean, we are about 0.96.
8 sigma.
So, and at 8 sigma. So, and this is when I said, can we improve the Doppler boost results? See, if someone tells me that the NS is known at 8 sigma now, to be away from 1 at unity, which is your scale free, it's heartening because you know that you're in the right direction. It is like an almost infrared divergence, but slightly tempered. So these are very important results.
Okay, one last question. This might be a bit naive, but when you talk about that Doppler boost, you're saying that in the direction that we are moving, we are sort of like we're pushing it forward, and behind we are sort of expanding it. But I mean, if I think about it from a sort of SR perspective, like, are we looking at some length contraction perpendicular to our velocity? Like, how do I interpret it?
No. So this is, remember that when special relativity was brought in, there were a lot of people, I mean, because of Michelson-Morley experiment, right, there are lots of ways people tried to explain it away. One was this ether drag and things like that. So these were ruled out because special relativity gives you this stellar aberration. So the positions of the stars, and you can see that even with 30 kilometers per hour per second movement of the Earth, right? So that that was the accuracy. It's an amazing thing that we don't pay attention. Michelson-Morley experiment looked at things at the level of 10 to the minus 8. Right? It was V by C of 30 kilometers per second squared, right? So that's what you need to make yourself permanently known in science. So yeah, so I don't know whether I answered your question, but
no, but like my asking was like how do I understand the mechanism of contraction towards the front? Because like if I'm moving this way, and
it's basically the same effect as stellar aberration. So it's essentially, if you look at two directions like this and ask how do they transform under Lorentz transformation, you will find that the sky directions, bunch up in the front. And so, I mean, I know what you're trying to get at if you're looking at a scale and you're saying, yeah, these contracting more. I haven't thought about it, but if you can figure it out. But I I looked at it like a straightforward
Like the
mathematical
angles
transform.
contracting. So
Yeah,
to say,
so
from
it's
the side.
basically if you look at n hats
Mhm.
and then you ask how does the n hat transform under a Lorentz boost, you'll find that two n hats like this will come closer here. So they bunch up around that and then these ones expand out.
Understood.
Yeah.
Okay, thank you.
I mean, what I'm trying to also say is length contraction is, to me, is not something more fundamental than this aberration. It's the same kind of an effect, right? I mean, it has the same kind of status.
Thank you so much for the wonderful talk. So I was wondering, like in the Bayesian estimation of the BIPOSH spectra section, so what are the various factors which are contributing to your noise models, and whether it could lead to, I mean, modulation of the noise model, whether it could lead to some improvement in the base factor that you mentioned in the estimation?
Yeah, there is some possibility there because, but not for the temperature fluctuation as much as from the polarization. So what you might have thought is we have actually very beautiful looking CMB polarization maps, right. But why didn't we look at that? We have papers which looks at exactly the same effect in that. The reason we didn't do it is because at large angular scales, the polarization data of Planck is systematic ridden. Okay, and it's my personal belief that I don't touch anything which has systematics, which is why I never worked on the high redshift supernova data ever, which was trivial to do. But the point is, it was known to be systematics driven, right? So it's a bit risky in my opinion because you can make a lot of claims which are essentially coming because you poorly understood the systematics. In CMB, one of the advantages is all linear physics. Even the detector thing, I mean, even the non-triviality of the Planck polarization is because it was not designed to be a polarization experiment. There were some kind of problems with the analog to digital conversion, and that's the only nonlinear part which is actually causing us, whose understanding wasn't at a level which we could.
So the terms in the noise model, so one part would be the instrumental systematics, but there would be the other, I mean, there could be cosmological sources also, right, in the noise models.
So a question is, so if it aligned with the dipole or something,
right,
you worry about it. Right. It's very difficult to see how the dipole can, and also if you look at it, it's an enormous effect. This Doppler dipolar modulation, if you compare in terms of bipolar strength, in fact, when we measured the Doppler boost effect, we removed the first 800 multipoles just to be sure that we are not contaminated by this, because it's a very strong effect. It's only that the statistical significance cannot be large because you have very few modes. So that's an important thing, but it's still worth worrying about, and we do worry. And I should also say, with many of these so-called weak level interesting deviations from standard cosmology, the point is they are at large scales, so you are limited by cosmic variance. I always worry whether we are doing the inference correctly, because if I have a sample variance, of course, you will say increase the sample, right? But if you are fundamentally limited in the sense that you are on a sphere and you can't increase the sample, then are we really right in saying that you can't say anything better, or is there any other way? I mean, again, we have been in a lot of debates within the collaboration itself on look elsewhere effect and things like that. I mean, it can be interpreted in many ways, and I'm happy to discuss. I mean, these are actually very important issues. I think we have not paid that much attention to it.
Thank you. Thank you so much.
Any other questions?
In the sections where you describe the bispherical harmonics, You took tensor product of spherical harmonics. So my question was, what was the need of bispherical harmonics?
Oh, that is because if you have a 2-point function, okay, on the sky, then it's a function of 2 directions. Now, if it just depends on the angular separation of the two, then it doesn't matter which pair I'm looking at as long as it's the same theta, right? But if they independently depend on this, that means the correlation function has directional information, then you will have the issue that the Legendre transform is not enough. So this bipolar thing is just the higher or natural generalization of a Legendre transform when you have dependencies above c theta. And I came across this, actually I was pointed to this by people more from atomic and nuclear physics, because there you worry about these couplings and things like that. So many of the bipolar things have been actually in the domain of nuclear science people, and we still so anytime you have, so if you have multiple nuclei, then you can't have a YLM like a hydrogen atom. You have YLMs, but if you have 2, you have to worry about the angles from both.
In this spherical harmonics, is they follow any Lie algebra, special Lie algebra?
No, it's just it is basically a product of YLMs. So essentially, it's a tensor product. So whatever it has is a trivial product of things. So I don't think there's a new symmetry a new kind of algebra coming out there. It obeys the standard algebras of SO3 or whatever you want to say. There's no big surprises of that kind or anything. It's not a different group, it's a product.
Any other questions? I have a follow-up simple question, follow-up question from Pratik's question. That thing is that after Planck 2015, the reason you didn't do it in Planck 2018 because of HFI polarization has a systematics and you...
I didn't use polarization data at all.
Okay, at all?
No,
because of the systematics?
Never, because essentially the worry I have is, even if we see something, I can't say anything. It's a nice paper to write, but
nobody else outside your group also hasn't tried this thing with polarization?
I haven't checked, but I don't think so. Again, due to other commitments, I have not been very conversant with the literature, but I don't think anyone has. See, anyone who knows the data well would worry about inferring on large angular scales from Planck.
Okay, yeah.
But people have done. I think there have been Italian groups which have not looked at this problem,
okay,
but they have used large angular scale thing. But I am very uncomfortable doing that.
Thank you. So if there are no other questions, let's thank Professor Sauradip again.
Thank you.
So we'll be having a high tea right outside. Okay, please join us.